in this talk, we will focus on the one key component in a traditional recommender system, basically the model training part. And this part is a model that we call GLMix. It's generalized linear model with mixed effect, and it's designed specifically for large-scale response prediction. And here are my name is Shenxing, and here are my co-authors at LinkedIn. So the first thing is, so why do we care about GLMix? Why LinkedIn care about GLMix? So there are so many different machine learning algorithms out there, like matrix categorization, deep learning, tree models. So why GLMix? So one reason is very simple. It works at LinkedIn's context. For example, so one of the core business at LinkedIn is job recommendation, right? We want to recommend job to our LinkedIn members. And GLMix is a model that is launched on the jobs homepage that gave us 20 to 30% lift in terms of job application rate compared to our previous model. And this model GLMix model is currently ramped to 100% traffic to serve all of our members. So if you go to LinkedIn website and click on jobs homepage, and all the job recommendations are now served by GLMix algorithm. And not only jobs homepage, so GLMix is also widely used in other products on LinkedIn now. A few examples include article recommendation, sponsor updates, aka just ads CTR prediction, and also a module we call people view this also view. It's basically an item-to-item recommender system. So GLMix is widely used on LinkedIn now, but let's go back to step back a little bit to think about, I want to present our thought process as we came up with the model GLMix. The question is why GLMix? So at LinkedIn, in nowadays there are about 6 billion people in the global workforce, and LinkedIn's vision is to provide economic opportunity for each of them. And in order to turn this vision into reality, so we are trying to build the world's first economic graph in order to turn this vision into reality. In this economic graph, each node we can correspond to, for example, a LinkedIn member can correspond to a company, can correspond to a job, a skill, and for example, influencer, a knowledge, and we want to connect all of them together. In order to do this, we need powerful machine learning models. And here are some good properties or desired model properties we realized across the years that we want to have. The first one is the model needs to be interpretable with the features. As we know, at the LinkedIn's economic graph, each node contains very carefully handcrafted engineered features, so which our models can utilize those features and give interpretable results. So folks can just take a look at the model and understand the graph better. The second is trivial. I think everyone should be comfortable with this. Is the model should be scalable, right? We don't want to build a toy model that's run on a single machine and that's it. So we want our model to be scalable. Another thing very important in industry is we want our model to be deployable, right? Deployable meaning that we want our models can be deployed using existing, aka for example, open source infras. So we don't want to come up with a model and then design totally new infra in order to launch this model. That may take then the development cycle might be months or even years, right? So we want to have a model that can just be a new model can directly be cast into the existing infra. And lastly, we want our model to be fine-grained. So this point is actually the key of this model and this paper. So we'll address this in deep. We'll dive into this feature later. But in general, the fine-grained meaning that we want to have the model to be adaptable to users with more data or those popular items. For example, on LinkedIn, we have active job seekers and passive job seekers. For those active job seekers who are actively looking for a job, we may have more data for them, so we want to have our model to better adapt to their behavior. So the first model we are going to look at is generalized linear model. I think in the previous talk we mentioned general linear model is already being covered and implemented in Spark MLlib. So generalized linear model is very simple. Everyone should be familiar with this. But the only thing we want to have folks to take a note is on notations. So some of the notation will be used in the remaining of the slides. So just use this example to introduce our notations. So here our problem is we simplify our problem into into this case, we want to predict the response of user I on item j. And Yij is the response. And here we're modeling the expectation of the response transformed by some link function, right? And the model is a linear model, meaning that it's a linear combination of the features. Xij is a feature for like user on item j, W is like the coefficient we learn. In this particular case, for example, I'll give you one more concrete case. If this function corresponds to a logit function, then this model becomes logit regression. If G becomes an identity function, it does nothing, then this becomes a linear regression. But here in this paper, we want to, instead of talking about a specific model like logit regression or SVM or Poisson regression, we want to like just use this notation in order to say, okay, this model is general enough to be applied in different type of data, whether it's binary, real, count, whatever. And of course, for this model, it's interpretable, it's using features, and it's scalable. A lot of algorithms and papers are discussing how to like scale up linear models, and it's deployable because this is like one of the most popular models across different companies. People already know how to deploy such model. So only thing in question is whether this model is fine-grained. We call it fine-grained, meaning that if we want to look at the model not only at the global level, we want to look into the individual users. For those users with more data, we want to adapt this model to that particular user. So here's one example. In this talk, I will use like the job recommendation as a running example. In this case, I say this is the data we have. And to simplify the problem, I say we have two users, Alice and Annie. And they are both looking for like a job, like a data scientist job. And we have this is like more like a historical log for those two users. For example, in the past, Alice has applied for data scientist like job at Microsoft. And Annie, on the other hand, applied some job, for example, at Airbnb. So, for example, let's say if Alice and Annie, they are actually with similar background. For example, they graduate from the same college, have the same major, they have some similar skills, and to some, they maybe in a feature-based model, they may be represented by those features that are very similar, right? Maybe their feature, based on a feature perspective, maybe they are very similar. And in this particular case, since if we are only looking at like the generalized linear model, which is the only model we are going to learn is W, in this case, it's very likely that we can learn nothing from this particular example. Because like Microsoft is applied once and didn't get applied, and Airbnb also get applied once, right? So it's very difficult to learn any useful information with like a model like GLM. And there are a few other alternatives like matrix factorization. Matrix factorization is a model that we also formulate matrix factorization is slightly different from the traditional like formulation for matrix factorization in that we are also using a link function here, just trying to say, okay, for the matrix factorization, it doesn't necessarily need to be a like alternating least square based approach. It doesn't need to be a square loss function. It can be a logistical loss function. It can be a hinge loss. It can be Poisson based. So here's the matrix factorization. So instead of learning a linear combination of the weighted combination of the features, matrix factorization is trying to embed like the users and item into a latent space, and they are represented by those two latent vectors, UI and VJ. So that's matrix factorization. So matrix factorization is scalable. There are many algorithms out there to scale up matrix factorization. It's deployable. It's well understood. It's a problem that is well understood. It's fine-grained in the sense that actually here we are modeling. So for each user, we have a latent representation for each user and a latent representation for each item. So with more data, like for those popular items or active job seekers, we can get more data, and those UI and VJ can adapt to those users. The only question is that MF, like a vanilla MF, I'm not talking about like all those advanced fancy version of MF. If it's a vanilla version of MF, it doesn't utilize features, right? So in our case, and because we are working, our economic graph has so many rich features, and we want our model to be able to utilize those features, and so that our modelers and data scientists can interpret the model. So that comes to our model. So we want a model, want a model that is interpretable, is scalable, is deployable, and fine-grained. So here comes GLMix. So what is GLMix? GLMix is also a generalized linear mix model. The keyword mixed, meaning that here is a model. Here's model is we actually, the first part is still the linear weighted combination of the features. And what's different from the GLM is we have a per user coefficient and per item coefficient, meaning that for each of data point, it's not only modeled by like a global coefficient W, it's also modeled, for each user, it's modeled by its per user-specific coefficient and item-specific coefficient. So this is also related to MF in the sense that in MF, so everything is in latent space, right? We are embedding like the users and items into a latent space, but in GLMix, right? For this particular, for example, in the per user case, the user coefficient is latent. We want to learn the user coefficient, but the items are represented in the feature space instead of a latent space, and vice versa in the per item like model. We have observed user features in the feature space, and we're learning like the per item coefficients. To sum up, GLMix is very simple to understand. GLMix equals to GLM model, like the logic regression model, linear model, plus two specific models, like per user model or per item model. So this actually also a very special case of GLMix. So GLMix actually can have infinitely many number of like per ID components. For example, we can build a per company model, like a per country model, a per region model, right? A per title model, and so on and so forth. But here, for the ease of presentation, here we only focus on a special case of GLMix where the model consists of a global model, which is GLM, a per user model, and a per item model. In the next, we're going to use one more very concrete example to help folks understand why GLMix works and what is GLMix using job recommendation. For example, here's still our model, right? We are modeling the expectation of the response, and it's like transformed by some link function. In this case, the global model is same as usual. It's like our old business. We have some features like, for example, similarities between the jobs and the member profile, right? At LinkedIn, we have very good, clean and good data, which is a member profile. And for each job poster, they will have very detailed description of what the job is, what the required skill is, and what is the functionality of this job. So we have those features available. So one natural thing to do is we want to compute the similarity between the member profile and job profile, for example, using something like cosine similarity. Right? The global model basically asks the question, do the member skills and, for example, do the member skill and job skill look similar? And for the second part is for per member model. It works in this way. For example, if a member has applied to a job with title software engineer, and of course, we want to boost all the jobs with title like software engineer in her result, because we know as we get more data, we are also knowing the user better, and we can provide the data or can provide the recommendation result that is more casted to the user's preference. Same thing goes for per job model. For example, if a job got applied by a member with title, for example, again, software engineer, and in this case, the per job model will boost the job more to those members with title software engineer. Right? That's meaning that for those popular jobs, we can get a better sense of how, what type of group of people is more likely to apply this particular type of job. And this thing cannot be achieved by the global coefficient, because global coefficient is measuring global patterns of across all the similarity type of features, and by using those per member and per job model, we can get a more fine-grained modeling of our data to look deeper into our data and to understand our member and job better. So let's revisit our previous example, Alice and Annie's example. Recall that Alice and Annie, they are both looking for a data scientist position. They have very similar background. They have very similar member profile, meaning that the X-Alice and X-Annie are very similar, right? But they applied different jobs. For example, Alice tends to apply for more big companies, and Annie is more preferred to those hot startups. And in this particular case, right, previously, since we're only having a GLM model, which is governed by a single global parameter W, in that case, W may be, like we discussed earlier, maybe 0, because there's nothing too much. The data just cannot capture the pattern. But now, since we have a per member model now, what happens is, for Alice, we will have a coefficient specifically learned for Alice and the coefficient specifically learned for Annie. In this particular case, then we can capture, okay, then in this particular case, we look at the first two rows, we realize, okay, Alice may tend to like the big company more, and maybe Annie tend to like the startup more. And in the next recommendation result, we can adapt the model such that we will recommend more big companies to Alice, for example, IBM or Google, and we may recommend more startup-like company to Annie. For example, we recommend Uber, Pinterest, or Snapchat to Annie. So to summarize, we just covered what is GLMix and what does GLMix do and what is the drawback of like the other like model like GLM. And now we see GLMix is still interpretable because it can be interpreted as GLM model plus a per-user component plus a per-item component, and it's fine-grained because we can look deep. We can look at the we can capture signal at the individual level, either it's per job or per member. But the next question is this model scalable? So we still want to, in order to have a good like model that can be launched in like our like core business, like a job recommendation or like CTR prediction for ads, it needs to be scalable. So here's so next we'll switch our focus to discuss the scalability issues for GLMix. So here's one simple example of just get you a sense of what is the scalability challenge for GLMix, right? For example, remember we have let's say if we only have a per user model, let's forget about per job model. Let's only have per user model. For example, we're only dealing with, for example, 10 million users, and we are only using, for example, 1K feature. In this case, since we're having 10 million models, each with 10,000 like feature, 1,000 features, in total we have 10 billion coefficient. So what if we want to like ramp the model to serve more users? For example, we want to serve for like 3 billion users. What will happen? Then the scalability will become a big issue. And here, since in this presentation, we don't have enough time to go into the details of how we actually scale up the model. So here's the sketch of the solutions. The first thing is we design some locality-aware data pre-partitioning, meaning that we want to shard the data by both the rows and columns. Each row in the database perspective, each row corresponds to an example in the training data, and each column to correspond to a specific type of feature. So we're having some context available. We have some context. We have some locality-aware data partitioning such that we want to minimize the network communication. And we also designed the algorithm. It's not a new algorithm. It's a very old algorithm, coordinate descent, and we casted this coordinate algorithm into a framework such that we don't need to shuffle the data. We don't need to shuffle the model at all because the data is large, and in our case, model is large. So we will keep the data and the model in their place, right? We'll never like move them across network, and only residual will be shuffled. So more details on how like coordinate descent will work in this case, how can we minimize the communication costs details can be found in the paper. Right, here's just a quick example of like the scalability of our model. Just simply put it, for example, if we have just like if we can put like more resource and cluster machine into our cluster, we can either handle more data gracefully, and we can speed up the model training time if we have fixed data size. So that's a message we want to deliver here. So now the next question is it's actually a big question. This is actually the most important question we want to address in the recommender system is how to deploy the model in production. Whether it's deployable or not, can we like deploy the model using existing, for example, open source infra? Right, so this is a question we want to answer, and actually this is the most challenging part in our real life. We spend, for example, when we design the model, maybe we spend like 1 month or 2 months to get the model working and get everything working. But how to like deploy the GLMix model into real production? How to serve our like 400 million members? That's a very difficult problem. So to summarize, I will not be able to go into the details for how to score the model, how to like deploy the model. I just gave some high-level introduction. So we have in general, we have two types of schemes in order to deploy your model. One is like we do offline scoring, one is online scoring. Offline scoring meaning that we prepare the scores for each of the user item candidate pair. We prepare the candidate set offline, and we score them and push the score into online key value store. right? In this case, since it's offline, so we can do whatever we want. We don't have any latency requirement. The only thing we need to care about is the throughput. So how many, meaning that how many like candidates and item pairs we can handle in our system. The other part is more interesting one is online scoring, meaning that we will somehow we want to store our model coefficients online. For example, our per member coefficient and per job coefficient. We want to store them online in some fashion, and the scores. So and the candidate set for the user and item pair are generated online and scored online. But the key part, the most intriguing and difficult and challenging part is latency. We want to minimize the latency, right? We don't want to serve a fancy model online and let the user wait for a minute in order to get a recommendation result, right? We want to serve a good model that also minimize the latency in order to serve the model. Right. Here's a sketch of how we do the offline scoring. So the details are covered in the paper. Basically, offline scoring is very simple, right? We divide our world into online world and the offline world. And offline world is handled by Hadoop. So we prepare the candidate set offline and score the candidate set with our model, and we get the scores for each of the user item pair, and we push them into online key value store, which is the Voldemort store in our case, which is an open source, a very scalable, efficient online key value store, and then we serve the model in that way. Right. However, there are some problems with owning the offline scoring. GLMix can only ramp to 8% of the traffic. We cannot handle 100%. So here comes how online scoring for GLMix comes into play. So I'm sorry, I apologize. I cannot cover this very interesting part in this talk. So actually, how to build a recommender system from end to end. One of the very challenging part, like I mentioned earlier, is how to do the online scoring, how to deploy the model online. So I encourage you to check out our hands-on tutorial, how to build an end-to-end recommender system with PhotonML. Just Google search the keyword PhotonML, and you will go to GitHub, the wiki. We have the wiki for the PhotonML tutorial. And with the online scoring, we'll be able to serve this very complicated and big, huge model with 100% of our traffic. To summarize, so GLMix model, it's interpretable, it's scalable, it's deployable, and it can model fine-grained data. Takeaways, so GLMix is, so here's what is GLMix. It's like I mentioned, and importantly, we want to say GLMix, so everything covered in this size and everything we're running in production now is open source. It's open source as part of the library we call PhotonML, and PhotonML is also implemented on top of Apache Spark. So we got a lot of help from folks from Databricks and Shangri, and folks helped us along the way to build everything on top of Spark. So yeah, let's conclude my talk and open to questions now.
Thank you very much for that. There's a question right up here.
So thanks for the talk. It's very great that we know the model is interpretable, but I have doubt when you have a lot of features, right? Mm-hmm. And then the features might correlated with each other.
Yes.
And then what if your alpha or beta is correlated with some of the features? Would it still be interpretable if the estimate is not stable anymore?
Yes, that's a good question. So this question have two related answers. So first of all, so in the GLMix model, actually it's I didn't go to detail, but this model is a well-studied model in statistics literature. So it's basically a random effect model. So for this model, what we learn is not necessarily, it's not just a coefficient. We also learn the variance for this parameter. For example, the variance could be a covariance matrix. By looking at the covariance matrix of the learned coefficient, then we can get a better sense of how those features are correlated. That's the first thing. The second thing is if you only look at the coefficients, yes, they will, if they are highly correlated, we may not make very accurate prediction or understanding of those features. But I would say it's better than nothing, right? It's better than we have no interpretation at all. So yeah, so in our company, so if folks are really want to understand the feature very well, to understand their correlations, they've been looking into the covariance matrix that we provided. Yeah.
Okay, thank you. There's another question in the back.
So my question is actually related to the previous question. I was wondering if you tried any any transformation or anything that handles the collinearity prior feeding the features into the model to
Yes.
address the same.
Yes, that's a great question. So collinearity is a very difficult, challenging problem. So what we do is we don't have very good solution for that. But what we do is we put regularization on it. For example, if those two features, there are two features like identical two features that are highly correlated. If you put like a L2 regularization on top of them, then both of them will get half of the weight if there's only one feature. So that's the only way we deal with like collinearity. Just put like regularization, like L2 regularization on it, make it a convex problem. So there's only unique solution. So that's what we do.
Thank you.
There was one last question over there. Maybe the next speaker can already start setting up, please.
This is a very interesting talk. Like this kind of combinations of the global model with the personalized model stuff. One of my questions is related with the more open discussions for this job recommendations.
Yes.
So we're more talking about career growth. So everybody think about they're doing today and is going to do something even better tomorrow.
Yes.
Whatever the model you actually described today is coming from the previous behaviors of the users, right? Is there anything you actually put into this kind of growth intention of your develop your career intention into the model?
Yes, that's a good question. So again, there's two answers to that. The first answer is, so our model is, what I didn't mention is our model is retrained daily. So, thanks, Alex. So our model is retrained daily, for example, for the job, not only for members. For example, if you like the job, there are new jobs every day, and each job will expire, at LinkedIn, each job will expire in 1 month. So in order to keep all the new job coming, or to capture all the new signals and new features, so the model is retrained daily. Actually, it's retrained every 5 hours. So the second question is for the user growth. Actually, currently this is done by feature engineering. So on LinkedIn, we have some data scientists looking into the problem. They want to like predict, for example, giving the user's current company and her current position, want to predict what is most likely she will apply to. First thing is, will she like consider changing her job at some time point? If yes, then what type of job she might be looking into. So those type of things are captured by features in our current case. That's why we said on LinkedIn we have a lot of like well handcrafted features. So we want our model to fully utilize them. Yes.
Okay, so let's thank the speaker again.